Hi everyone, I hope that all of you are okay and feeling well. Mrs. Diham Said speaks from the Egyptian language school in Doha, Qatar, and today I'm gonna introduce a new session with the chemistry curriculum for the first term. As you know, we study Unit 2, and in Unit 2 we study the structure of the atom and the different attempts made by different scientists through many years to reach the most accurate structure of the atom. So the title of our unit is the atomic structure. My dear students, in Unit 2, we discuss the different attempts made by the scientists like Thomson. Thomson, if you remember, the scientist who he gave us a model for the atom, but it was not very accurate. He didn't conduct any experiments to prove his model of the atom. It was an attempt without any experimental base, so it was not successful. It was not very successful. So we usually start the atomic structure with Thomson's atomic model, which was a model which didn't depend on an experimental base. Let's start with the first question in our session. By the way, today we revise the most important points mentioned in the school book exercises, okay? First question in our lesson today, explain each of the following. Number one, Thomson's atomic model. As we know, Thomson was a scientist who didn't conduct any experiments, so we consider it as an attempt without any experimental phase. There is no experimental phase. He didn't conduct any experiment. The model for Thomson, or the effort of Thomson for the atomic structure, he described it as a solid homogeneous ball containing positive charges and negative charges. The positive charges are the protons and the negative one are the electrons, and the number of positive protons is equal to the number of negative electrons, which makes it to be considered as a successful attempt to some extent. It didn't depend on an experimental base, but the right point here for Thomson, he was lucky to be the first scientist to prove that. He was the first scientist to prove that the number of positive protons inside the atom is equal to the number of negative electrons which revolve around the atom, making the atom as a neutral ball of positive and negative electric charges. This is for the first question concerning Thomson's atomic model. He considered the atom as a homogeneous ball. This ball is solid homogeneous ball of positive and negative electric charges. And the number of positive charges is equal to the number of negative charges, which makes it electrically neutral. And now we come to another question. Question number two, explain. Question number two asks you to explain Rutherford atomic model. Rutherford atomic model. Rutherford was the first scientist to make some experiments. He made his famous experiment. This is the first model for the structure of the atom, depending on experimental base, which made it as a very successful attempt. He was the most successful scientist to prove the atomic structure. And after that, we will discuss the experiments which was conducted by two of his students, as you know. Now we come to the third question. In the third question, we discuss the line spectrum, or what we call as emission spectrum. My dear students, let me remind you that if we have a pure element and we heat it at high temperature and low pressure inside an electric discharge tube, the element will emit number of restricted colored lines, and these lines are separated by dark areas. We have some lines or some colored lines. Between each two lines, there is dark area. This is a dark area between the colored lines. Okay, dark area, then dark area, and then dark area. This is called emission spectrum. So the emission spectrum is a it is a group of colored lines separated by dark areas. This area is dark, this area is dark, and here is another dark area. This dark area is characteristic property for any element. No two elements have the same line or the same emission spectrum. It differs from one element to another. So we say that it's like a fingerprint. We describe it as a fingerprint, okay? And now we come to the line spectrum for hydrogen atom. Hydrogen atom, or the line spectrum of hydrogen atom, I mean this question here, we ask about the line spectrum of hydrogen atom. As we know, any line spectrum or any emission spectrum is a group of colored lines separated by dark areas. But how many lines are emitted from hydrogen atom in its gaseous state as a pure element؟ ما هو أنا عندي conditions معينة عشان يحصل لي line spectrum أو for the element to emit its emission spectrum. I have to heat a pure element at high temperature, at low pressure, inside an electric discharge tube. And if we do these conditions or this experiment with hydrogen, we observe that the line spectrum for hydrogen atom consists of 4 colored lines, and the colored lines which are emitted from the hydrogen atom are red, green, blue, and purple. These are the 4 colors emitted by the atom of hydrogen, okay, that we call as the line spectrum of hydrogen ion. And please don't forget the line spectrum or the emission spectrum looks like the fingerprint for each element. It differs from one element to another. Let's come to another question. My dear students, we have studied the modern atomic theory. You remember the modern atomic theory? The modern atomic theory includes some corrections or some modifications made by Heisenberg, Schrödinger, and also de Broglie to correct some of the drawbacks عشان تصحح لي بعض drawbacks أو shortcomings في Bohr's atomic A model. From these modifications, the dual nature of the electron. We know that one of the drawbacks واحدة من drawbacks أو من disadvantages بتاعة البور atomic أو Bohr's atomic model, he had to deal with the electron as a negatively charged particles, and he ignored his wave properties. And here, the dual nature of the electron corrects it. The dual nature of the electron considers the electron as a material particle, I mean negatively charged particle. I'll consider it أنا هقول إن هو negatively charged particle, but I never neglect its wave properties. So the dual nature of the electron states that the electron is a material particle with a wave properties. This is for the concept of the dual nature of the electron. And now we come to the Aufbau principle. What does it state? Before we discuss it, let me remind you that S, P, D, and F are called the sublevels. For the electrons to fill these sublevels, and according to the Aufbau principle, which is called the building up principle, we call it as Aufbau principle or building up principle, it states that the electrons fill the lower energy levels before filling the higher energy levels. So we call it as building up. I build up, I mean from the lowest energy to the highest energy. This is for the Aufbau principle. For the Aufbau, we can say also the Aufbau principle states that electrons fill the sublevels of the lowest energy before filling the sublevels of the highest energy. Here we have lower energy sublevels, and higher energy sublevels. As a building up, I move ascendingly from the lower energy sublevels and then to the higher energy sublevels. So the sublevels are arranged in an ascending order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. This is the ascending order, I mean, from the lowest energy sublevels to the highest energy. And this is the Aufbau or the building up principle, which states that electrons fill the sublevels of the lowest energy before filling the sublevels of the highest energy. And now we come to the uncertainty principle, which was proposed by Heisenberg. Heisenberg was a scientist. He had to correct the drawback or the shortcoming. بدأ يعمل لي correction على ال disadvantage بتاع البور's atomic model. He had to correct the drawbacks or the shortcomings for Bohr's atomic model. Bohr stated ايه بقى الwrong او misconception بتاع بور اللي بدأ يعمله correction, which was corrected by Heisenberg in his uncertainty principle. Bohr decided that it is practically possible to determine the location and the speed of the electron accurately around the nucleus, and this is practically impossible. I can never determine the speed and location of the electron around the nucleus accurately. I discuss it in the term of probabilities. I'm not sure. No one can determine the accurate location and the accurate speed of the electron around the atom. This is one of the misconceptions, one of the drawbacks, one of the disadvantages of Bohr's atomic model. And Heisenberg, in his modern atomic theory, he came to correct this misconception. بدأ يجي الهايزنبرج uncertainty principle عشان يعمل correction for the misconception of Bohr's atomic model. What does it state? بيقول لي ايه الهايزنبرج uncertainty principle? It states that it is practically impossible to determine both of the location and the speed. By the way, I can say speed or velocity, okay, of the electron, but we can say it's less likely, less or more, by the way. We discuss it, it's just possible. I'm not sure. No one can practically determine the speed and location or the velocity and location of the electron, and this is the uncertainty principle, which was proposed by Heisenberg in the modern atomic theory. A new question in our session today, which is Pauli's exclusion principle. Before we talk about Pauli, let me remind you that we have 4 quantum numbers. N is called the principal quantum number. L is the subsidiary quantum number. ML is called the magnetic quantum number, and MS is called the spin quantum number. So we have principal quantum number, subsidiary quantum number, ML is magnetic quantum number, and MS is called the spin quantum number. For two electrons in the same atom, the four quantum numbers can never be similar. Again, in one atom, the four quantum numbers can never be similar. No two electrons in the same atom can have the same four quantum numbers. They may have the same principal quantum number, the same magnetic magnetic quantum number. They may also have the spin quantum number, but they may be different in the subsidiary quantum number. They may be similar in three of the quantum numbers, but they should be different in one or more. Generally, عشان نختصر الموضوع ده, no two electrons in the same atoms can have the same four quantum numbers. They may be similar in some of the quantum numbers. They may have the same principal, the same subsidiary, the same magnetic, or even the same spin quantum number, but the four quantum numbers can never be similar for two electrons in the same atom, and this principle was proposed by Pauli, so we call it as Pauli's exclusion principle. And now we come to a very important question. What are the possible values for L? Letter L means the subsidiary quantum number. The subsidiary quantum number here is our question. We don't know what is the expected or the possible value for L. And the value of n, I mean the principal quantum number, is given as 3. My dear students, in the third level, in n equals 3, so we have the following sublevels. We are in the third energy level. يعني حضرتك موجود دلوقتي في level M اللي هو ال third main energy level. So N includes 3, S 3, P and 3D, because each main energy level has number of sublevels equals its number. We are in the third level, so we have 3S, 3P, 3D. These are the sublevels included in the principal quantum number 3. So the subsidiary quantum number for S equals 0, and for P equals 1, and for D equals 2. So the expected or the possible quantum numbers for the L, I mean the subsidiary quantum numbers for this level, I mean N3, are 0, 1, and 2. 0, 1, and 2 are the subsidiary quantum numbers here. So the right answer for this question is we are in the third main energy level. N equals 3, so we are in level L or K or M. tell me. N equals 3 يبقى أنا في أنهي main level؟ KLM يبقى أنا موجود في level 3 اللي هو level M. level M. Each main level includes number of sub-levels equals to its number. يبقى at level M اللي هو third level أنا عندي 3S, 3P and 3D. So the subsidiary quantum numbers will be 0, 1 and 2. 0, 1 and 2. So let me write the possible L values. They will be the expected values for L. L may be 0 and 0 for S sublevel, 1 for P sublevel, and 2 for D sublevel. So the expected values for L, expected values, الvalues بتاعتي لل L اللي هو subsidiary quantum number عند third energy level يعني level M. And the three values 0, 1 and 2. 0 for S sublevel, 1 for P, and 2 for D sublevel. A very important question. Here I have boron atom. The atomic number of boron is B5. Let's write its electronic distribution. We have 1s2, 2s2, and 2p1. Ask yourself before you answer, where the last energy sublevel here, where the last sublevel here is 2p1, 2p1. So we have the last energy sublevel, which is 2p1, and as you know, the sublevel 2p contains 3 orbitals. Let's draw the orbitals. 1, 2, 3. We have only one electron. This electron will be placed here as a single electron because no pairing may take place. I don't have enough time. Sorry, I don't have enough number of electrons to make the pairing process. There is no pairing. So, the question now is to find. أنا دلوقتي عايز أعمل إيه؟ I'm looking for the quantum numbers for the last electron. Where is the last electron? Here, the last electron, which is found in 2p1. We need the principal quantum number. The principal quantum number is written below the sublevel. يبقى the principal quantum number 2. طيب, it lies or it locates in the p sublevel. واحنا عارفين ان ال p sublevel يبقى ال subsidiary quantum number بتاعه 1. And don't forget, I usually repeat, دايما بقول لكم ان ال subsidiary quantum number starts with 0. 0 for S sublevel, 1 for P, 2 for D, 3 for F. يبقى أنا عندي S, P, D, F, 0, 1, 2, 3. And because this electron locates in the sublevel P, so its subsidiary quantum number will be 1. And now we come to the magnetic quantum number. To determine the magnetic quantum number, what can I do? Here is the P sublevel. This electron locates in the P sublevel. And as we know, in p sublevel, we have 3 orbitals. At the middle, we put 0, and the number before it will be negative, and the number after it will be positive. You remember? So, the value of ml, اللي هي magnetic quantum number, equals, here the value is -1. ليه? Because it locates at the first orbital in p sublevel. And finally, so before we come to the spin, قبل ما اروح للspin quantum number, the value of ml equals -1. -1. And finally, we come to the last one, which is the spin quantum number. As a single electron, the spin quantum number for it, which is ms, equals +12. +12. Okay? So we have n equals 2 because it locates in the second main energy level. خلينا نعمل conclusion كده لكل الحاجات اللي عملناها. n equals 2. The principal quantum number equals 2. The subsidiary quantum number, which is L, equals 1 because it locates in the p sublevel. ml equals -1, and ms, I mean the spin quantum number, is +12. These are the 4 quantum numbers for the last electron in boron atom. So here's a principal quantum number, subsidiary quantum number, magnetic quantum number, and spin quantum number. My dear students, this is for the answer of our question here. Let's come to another question. The question now. Mention the four quantum numbers for the last electron in fluorine atom N9. طيب لما أقول quantum numbers يعني I need to find the value of N, I mean the value of the principal quantum number, the value of L, which is the subsidiary quantum number, the value of ML, which is the magnetic quantum number, and finally MS اللي هي the spin quantum number. Test yourself and answer this question, and please tell or send me the answer for this question on the messages of your team's account. Okay. In E11, we need to find the possible four quantum numbers for the electrons in sodium atom. First, I write its electronic distribution according to the building up principle. It will be 1s2, 2s2, 2p, 6, 2p6, and 3s1. Ask yourself where the last energy sublevel, here is a 3s1. So this electron, I mean the last electron in sodium atom, is located in S sublevel. And as we know, S sublevel has only one orbital, so it will be an unpaired electron or a single electron. Let's write the expected quantum numbers. The number which precedes the sublevel is the principal. يبقى أنا عندي البرنسبل كوانتم نمبر هنا هو النمبر which precedes اللي بيجي قبل اسم السبليفل، يبقى ال n equals 3، وعندي ال L اللي هي ال subsidiary quantum number. subsidiary quantum number for any electron in S sublevel بيبقى 0 يا شاطرين، وانتوا عارفين الكلام ده كويس. طب for the magnetic quantum number اللي هو ال ML equals from negative L to positive L. But the value of L equals 0. I can never say negative 0 and positive 0. There is no positive 0 and negative 0. So it will be 0. The value of the magnetic quantum number will be 0. And finally, MS, which is a spin quantum number, equals positive half. Why? Because it spins clockwise. So the value of the spin quantum number is positive half. Question in our session. Give reason for each of the following. The metal plate in Rutherford experiment was covered with a layer of zinc sulfide. My dear students, this is a very important question. Why the metal plate in Rutherford experiment is painted by a layer of zinc sulfide? Why? Because alpha particles are unseen rays, as you know. So we have to have a way, you have to detect them. I have to have an indicator. The rays of alpha particles are unseen. I cannot see them. So we paint the metal plate. Do you remember the metal plate? It is painted from inside, from here. It is painted with a layer of ZnS, zinc sulfide. Why? Because it glows up when the alpha particles collide, when the alpha particles hit it. So it will glow up. It will give some flashes to inform us or to make us attention that the alpha particles could penetrate the gold foil in Rutherford experiment. Number 2, most of the alpha particles pass through the gold plate without being deflected. Why? As you know, most of the atom is an empty space because there is vast or large spaces between the nucleus and the energy levels. So the answer for our question is that the atom has an empty space and it is not solid, as it was proposed by Thomson and Dalton. The atom has a great spaces between its energy levels, so most of the alpha particles can penetrate. Now we come to a very important question. And by the way, these questions are taken from the school book exercises. The line spectrum for any element is a special property. It is similar to the fingerprint for human. Why? Because there are no two elements with the same atomic number. And we confirmed it many times. Number three, the energy level, or sorry, I mean the energy sublevel P, the energy sublevel P is filled with 6 electrons. P sublevel contains how many orbitals? Do you remember? The P sublevel has how many orbitals يا شاطرين? P sublevel has 3 orbitals. And the full capacity for each orbital is 2 electrons. 2 multiply 3 equals 6 electrons, and this is the answer for our question. So we have 2 electrons in the first orbital. One of them spins clockwise and the other one spins anti-clockwise, like this. And for the d sublevel, you know the d sublevel contains how many orbitals? 5. 5 multiplied 2 will be 10. 1, 2, 3, 4, and 5. Each one of these orbitals contains 2 electrons as a full capacity, so it contains 5 orbitals, and p sublevel contains 3 orbitals. 3 multiply 2 يعني أنا عندي ال p sublevel contains 6 electrons وال d sublevel في 10. 10 means 5 multiply 2. 5 multiply 2. So the number of electrons that can fill any sublevel is determined by the number of its orbital. And don't forget that the full capacity for each orbital is 2 electrons at most. My dear students, we came to the end of our session. Let me say thank you so much for watching the video. See you later in our classroom at school next Wednesday. Thank you so much, and I hope that you have a good day.